All right. So I'm going to try to talk through this LSTM predictor in Max and training. And I'm going to do that I'm going to start first by playing some music. Yeah. So this is a neural network that has been trained on the Goldberg variations by Bach and the aria. And it's predicting pitches and durations based on the pitches and durations of the piece. So I'm going to try to talk you through this patch, which does the prediction and also does the training. So this says start here because it's a bit of a chicken and egg situation, and it's hard to say where the beginning of this patch is because there's a lot of feedback, and so this seems like the right place for me to start. So every time it receives a bang here, a note is made. So the metro is going through a counter, and the rhythm is controlling how high the counter goes, so how often a bang goes through. But every time a bang goes through, a note is made. So what happens here, there's a TBB, and it puts a bang out here and a bang into what next. The reset bang is important. This has to happen before each note prediction. And basically, this is because RTNeural is a stateful LSTM by nature. So this means that it retains its state every prediction it makes. This makes sense in audio because you have this stream of audio coming in and it gets a sample, it predicts the output, gets the next sample, predicts the output, gets the next sample, predicts the output. It's really important that it has a long tail of knowledge to know what happened in the signal as it's coming in. But in predicting notes like this, at least in this training, we want to reset the network every prediction. So first thing is reset. Next thing goes to what next. This is a really simple little logic where if I press this while it's going, it will just set that toggle, and on the next bang from the circuit, it'll switch back. So by default, what's happening is the input bang is just going out to the predict to do end notes and do end durs. But if this is triggered, it will instead send a bang up to the top of the network and grab a new chunk of audio or a new chunk of notes or a new chunk of rhythms to predict on. So it'll basically grab a set of 5 linear notes from here and send that through the next network on the next metro. And the reason for that is that it'll get stuck. Like as it's going, you can hear it'll get into a weird trill or it'll get into a rhythm that's just all twos. And the way to get out of it is just to find a new place in the network, and it just resets it from where it is. So let's check out the next thing it does. So what next, as long as this is triggered, goes through here. And what this is doing is it's storing the last 5 notes. So the notes are coming in on here, like each predicted note is coming in here. We have the last 5 notes stored here, and the next note comes in here. And all this is doing is basically pushing the last predicted note to the end of the list here. So if we 67's at the bottom, then it's up 1, then it's up, that's the third one, then it's the second to first one, and then it's the first one, and then it's gone. So this is every trigger the note basically goes in the bottom and comes out the top, and then this stores a list of the last 5 notes that have been played. This little JavaScript divides by max value. So there are the highest note in this sequence is 83. So we need to divide all of these by 83. It's very simple before we send it to the neural network. So like most neural network situations, the network is expecting values between 0 and 1. So if the highest value that it could possibly predict is 83, then we divide all the input notes by 83, and that means our input notes are between 0 and 1. Hope that makes sense. So that's do n notes, and so it basically takes the last 5 notes, divides them all by 83, sends them out. And where are they going to go? They're going to go to the LSTM predictor, or the note predictor. That is in here. It's in predict pitch. So it receives the 5 notes as a list, and it sends them to RTNeural. Now, RTNeural is in a, it says the input size is 1, and yet we're sending it a list of 5 notes. So how does that work? Well, it will take whatever the input of the neural network is, in which case this is 1, and it will internally grab the list of 5 and iterate over it and send each note individually through the LSTM network. So it'll basically do 5 predictions and then just give us back the last one internally. So even though this says 1, it is going to accept a list of 5. In a more complicated situation, if the network is expecting like 2 or 3 values, if it's expecting 2 and you send it 10, it's going to break those up into pairs. So it'll do the first 2, send those through the network, the next 2, the next 2, the next 2, the next 2, up to 10. If you send it something that is not divisible by the size of the expected input, it just won't work. Great. So this receives the 5 notes, sends it to the network, and what it outputs is something called a softmax. That's the output layer of the neural network, or that's the last output layer. But the output looks like this. And since our network goes up to 83, there are 84 values in this output. And what they are weighted probabilities of the next note. So those numbers represent a note, and every time we send a set of 5 notes in, every time we send a set of 5 notes in, it will give us like the most probable set of notes on the output. So what we're toggling here when we toggle, so the input of this will basically, this JavaScript takes this softmax, and it's going to output, you can see it outputs 3 things. The first thing is the most probable output, so in which case is 67. So it takes this, realizes these are integers, it multiplies them by 83 in this case, and then it gives us an integer output. The second output is the probabilistic output. So it takes this softmax output and it does a weighted random number event generator based on these probabilities. So it can get different answers. Yeah, so there's a perfect situation. So the most probable was 66, but the third most probable was 73. Second most was 69. So, but it looked at those values, and and you can see it here, 60. 6 is barely most probable. And it decided actually not this one, but this one. So when we toggle this, we're toggling between the most probable note and the weighted choice of notes. And I just put this out here just so we can see what's happening. So great. Same thing happens with durations. So do endures, the same process. Sorry, not that one. It's the same exact process, except the network is a size of 35 because there are only 35, or the maximum duration that was sent to it was 35. And it also has this most probable weighted output, and there's the softmax output for a 35 possible inputs. So that's what's happening every time. So how do we train the network? So let's do that. The training is up here. Make the data set. To make the data set, I'm going to move that so it's not crowded. So number one is clear the points. So we are going to make a data set internal of the inside the note prediction RTNeural object. So clear the points, and if I post the points, there are no points. No inputs, no outputs. Excellent. We need to make the inputs and outputs, and we're going to make them over here in our subpatcher. So first thing I need to do over here, how much memory are we going to base our prediction on? We're going to do 5. So we can just press bang there, and it will send that value around the patch to make sure that that everywhere knows that you're supposed to make you're supposed to grab 5 values before you send it to the neural network. Because if you send it the wrong size values, it'll give you an answer that just will be wrong. It might be wrong anyway, but it will definitely be wrong if you send it, say, 7 values or something. So then right here, we're going to clear the groups, and I'm going to make sure that this is getting from 2 max to max. And we're going to just listen. I'm just going to play this aria back. Okay, so that's what we trained it on, and we're just going to do it again. And now if I send those messages, those notes, all right, so that's fewer notes. I guess I had done a bigger set, but that's okay. So this is a smaller set, and I did something over here with the duration. So this is a bit of a challenge, right? So because this is a classical music piece that is a MIDI rendition that is super square, I'm doing something really simple where I'm taking the smallest duration, which are the trills, and I'm just dividing them all so that I get neat integers as outputs. But that's not always going to be the case. You might have to come up with a more creative solution for dealing with the rhythms. You want to have something that simplifies down to something like this, so that we can, do prediction on it and have it make some kind of sense. So let's train the pitches first of all. So if I press this bang, it's going to run through this JavaScript, which is get LSTM vectors. So what does that do? This basically iterates over the array and grabs 5 values, and those are the input to the network, and then the target will be 83, and then so 79, 80, but 83. Target is 81. So it input-output pairs where the input is a vector of 5 values and the output is a vector of 1 value. So if that's what this code does, it also gives us important information right here that we're going to need, which is that the maximum value of the list in here is 83. And that means that the math that we need to do, like we said in the other earlier, that we're dividing by 83 the whole time. The reason why we're dividing by 83 is because the maximum value note here is 83. And then 84 is the size of the output layer of the neural network. So the patch will send this 83 around for you automatically, but it won't. So if you want to use this to train something totally different and the highest note is, 97, well, then you have to go in and change the size of the neural network to the number that is represented right here, right? So the neural network, these things have to match. Great. So now if we post our points, we have 70 points. And we have 70, input vectors and 70 output vectors. And that's exactly what we want. We're going to set the epochs. And I know this does not need to be 3,000. We're going to make it much less. We'll make it like 1,500. We're going to set the learn rate, although it doesn't look at this. So you don't actually have to set that. And then we're going to set the layers data. And so, I'm going to write this. So the layers data is 100 tan H. So this is an LSTM. And so it's going to have a hidden size of 100 and then a tan H activation function. It's right now the script doesn't actually look at tan H, but you could write a script that does look at it. So this is actually, this is in this is interpreted by the Python code. So it could be, you could write something different than what I wrote, and you could have different Python code. So now we're going to write our JSON file. And so there's this in the examples folder for RTNeural Max, there's saved models and then LSTM note prediction. We're going to save it in here. We're going to call it Bach notes.json. Save. And now that we have our notes JSON, we can do our training. So what I'm going to do is I'm going to go into the terminal. Now I'm already in my folder and already in my virtual environment, but I'm just going to deactivate that for a second. And so say I'm not in RTNeural Python folder. So I'm going to change the directory to, not that, the RTNeural Python folder. Sorry, mine's on my desktop. And change the directory. And then I'm going to activate my virtual environment. So source venv bin activate. And when I do that, my environment gets activated and I can see it there. And then I'm going to run Python. And then the Python script is in the RTNeural Python folder. It's in this LSTM note prediction folder. It needs to be in this folder. Don't move it. It won't work. And the reason it won't work is because there is some Python code here that is looking at dependencies, which are right here in the model utils. So leave it in there, but we're going to drag it into the terminal, and then we're going to tell it where our file is, and that's Bach notes. Let's just look at Bach notes real quick. So it tells it what the epochs are, the invals, which are these 5 note vectors, the out vals, which are these one-note vectors. These need to be arrays, right? They can't be just individual values. And then the size of the neural network, 100 tan h. Those are the most important things, or those are the important things with this particular Python script. And when we run it, should take a second and then get training. All right, so it got done, got 90% accuracy, not so bad. So 9 out of 10. And it saved a Keras file, which is the TensorFlow format, and then it saved an RTNeural file. And if you look in this RTNeural file, it says that our in shape is null 5.1. That 1 means that's the size of the input layer on the neural network. And then the training is in here. So if we want to load that model, if I press load, I think it's going to load. Yes, and it does. So if it doesn't load, it's not going to say model input size 1, model output size 84. It'll say something like couldn't load the model. So now the one I was playing at the beginning of the video actually had more notes to it. It had the full first and second phrase, and this just has the first phrase. Not bad. So let's train the rhythms now. So there is a second RTNeural here, and this one's, notice it's send to LSTM predict. This one says send to LSTM dir predict. So what we're going to do here is we are going to clear the points, go back into our data set, ping the points, close this, go back over here, and if we post our points, this one also has 70 points. They're just different numbers, mostly 1s and 2s, 6s and such. Set the epochs, set the learn rate, set the layers, write the JSON, and we'll call it Bach dirs.json. Go back into our terminal. It's good we didn't close it. We're still in our virtual environment. All we need to do is press up and change the name of this file. And we'll do our rhythm training. Okay, it's done with a 94% accuracy. It was at 94% like way a while ago. Unfortunately, you can't stop this training and get the result, but it was there pretty much, you know, about 1,000 in, if that. Okay, so now we're going to load our model, and I think it might complain. Yeah, perfect. It said disabling model. Output size does not match the number of output channels. The reason there is because the maximum output, so before our maximum output was 35, but this is a smaller data set. And if we look here, the maximum output is 18. So that means the output size of the neural net should be 19. So I just need to go into my neural network and change it here to 19. All the other values should in the patch should be updated. Where we need to divide by 18, it should do so, like right here. That should be fine. So now, oh, I need to load the network. Duh. Okay, it liked it that time. Wow. Well, that's pretty weird. So you notice that like the training is very different than what I did at the beginning. And I think part of that is I kind of messed up, but it's actually kind of cool to see that the rhythmic training, especially with not as many values, it's really getting stuck in like 2s and 3s and 6s and stuff. And it's getting into these loops. It was much better when I had bigger data sets here. And all that was at the beginning was rather than playing just the first phrase of the Goldberg variations, I played like the first 2 phrases. Okay, so since that sucked, I'm going to do it again. And I've made a couple modifications to the patch, one being that this make data set is now up here. So it's easier to go back and forth between things. The other one being that the ZL group, the default max size is 256, and we're going to change it to 1,000 here so that it can actually get more than 256 notes. Otherwise, it will output the group, the list at 250 elements. So we're going to clear this. I'm going to do this again. Okay, so I recorded the entire melody, and if I press this, okay, so it's a lot going on there. Covers up a lot of what's going on, but that's fine. Now, the nice thing is we can actually train these 2 things at once. We don't need to do them separately because we can do them in separate Python windows. So I'm going to clear the points in both neural networks. I'm going to send the points, the input points and out points to both neural networks. And now if we post those, it should give us 463 notes, and post those, another 463 durations. And okay, we'll write the JSON. We'll call this Bach notes 2.json, and then we will write this one, and this is Bach-ders2.json. And if I go into the terminal, I did this already, so I have these open. But so on this left one, I'm going to do Bach notes 2, and on this right one, I'm going to do Bach-ders2, and they'll train at the same time. If you look over into Activity Monitor, where's the window? Yeah, if you look in Activity Monitor, they'll both be going at about 158% CPU, which is the maximum that TensorFlow does. So PyTorch will go up to 1,000%, or it'll go full GPU, but TensorFlow really will only go up to about 150%. Okay, the notes are done, 89% accuracy. The pitches or the rhythms are done, 90% accuracy. Let's load the 2 models up. Notes 2 _ RTNeural. That's going to load fine. This one might complain. Notes 2 DERS2. And it is, and that's because the data set, the size of the output layer needs to be 41 based on this data set. So we need to go into predictor and change the output size of the neural network. There's no real way to automate that, at least not that I know of. But now if I load the model, there's 2. Now it's happy. All right, let's see what this thing sounds like. So what I think is really interesting is every time I've trained this thing on slightly different data sets, even the same data sets, it acts differently. It has a different personality, right? Which is kind of cool. I mean, it's kind of frustrating because when you get a good one, you want all of them to be that good one. But this one is not as nice as the one I had a couple times ago. What can you do? But it also shows that the garbage in, garbage out with neural networks, right? When I screwed up the size of the neural network and only made a small number of values in the melody and rhythm sequence, then it wasn't quite as it wasn't accurate at all. And now it's a little bit more accurate. I think one of the other problems with this one, and I'll just change this so is that the 2s from before were the 1s before. So if I just change this, I think it'll play a little faster.